Caroline. Okay, I would agree. So,
We found points close to 5 and close to 2. So what's around it? 3.5.
So we took points. We found that this point was 2, 5, and then we took like the point. What was it? Did we do from below or above? I forget.
2.1 and 5.4.
Okay, so we did like 2.1 and 5.41, and we saw that the slope kept getting closer and closer to 4. Okay, yeah, we did do that, and we're going to do that. We're going to do that in a couple ways with this graph, and really, I guess. Well, actually, I should go back to the calculator. If I actually zoom in at, whoops, did not want to do that. Hold on. Let me go back to the graph. Let me trace at 2. And if I zoom in at this point, and if I trace and type in 2, and I zoom in, I think just one more time. What can you say about that function when we look really, really closely at 2? Say again? Yeah, it is. And this is a property of functions called local linearity, okay? And all well-behaved functions are locally linear. We're going to get to the point where we look at some functions that aren't locally linear, that as many times as you zoom in, you can't get it to look like a line. But this function actually looks pretty linear. And if you think about what we were doing yesterday, we were taking 2 points that were really close together. And if we take 2 points that are really close together, isn't that almost going to fit the function as a linear function? Does that make sense? So, if I take, yesterday we were taking 2 points that were really close together, like, these 2 points here. If I use those 2 points, you can see that the line that goes through those 2 points is almost exactly the line that goes through the function if we zoom in. And that's the tangent line. And actually, if I, let's see, I think I can do this. I'm gonna go back. Can I go back? Yeah, I think I'm just gonna go from 0 to 4 and from 0 to 10. I can actually figure out what the graph of the tangent line is. Because what point does the tangent line go through? 2, 5. So I know I can give you a point. And what's the slope of this tangent line? You told me what it is about. It's about 4. Caroline, how did we get 4?
Because we picked the 2 points and then we did this yesterday.
Right. So yesterday we picked 2 points that were close to one another, and we kept looking at the limit as we get closer and closer. We came up with the table. I'll show you some other ways of getting the slope to be 4, but right now the slope was 4. If I give you the slope and a point, can you give me the equation of the line?
Yeah.
All right. What do you want to? Can we use point slope form?
Yeah.
4 minus x minus 2. And if you wanted to, you could do 4x minus 2 plus 5. Or if you really wanted to, what's that? 4x minus 3. All right, so check this out. Going back to my calculator, 4x minus 3. Hey, look at that. There's the tangent line, right? And that tangent line has the same slope as the function has at that point. Now, can you see that, like, if I was talking about the slope at 1, it'd be, the slope at 1 is less than 4. And the slope up here is greater than 4. But the slope right there is exactly the same as the tangent line. And if I do it again, if I could, whoops, sorry, hold on. Trace to, okay, and if I do the zoom in now, what's going to be true about the function and the tangent line? Yeah, I mean, not only do they overlap, it should get to the point where we can, like, really barely differentiate between, right? See? It does. It does. And it only touches at that one point. But in the neighborhood around that point, it's really close. Like so close that your calculator can't tell the difference, so close that it's trying to show you that you can't tell the difference. But they'll actually only intersect at that one point. Even if we zoomed in a lot, it would be on top of it, but it's not telling you that they intersect in all of those points. It's just saying the calculator is limited in its ability to show you that. All right? Yeah, definitely. As a matter of fact, that's actually a great idea. If we went to the table and I went to table set and I started at 2 and I went up by can we just do 0.01? So, right, here's the function, 5.0401. Here's the tangent line, 5.04. What do they differ by? 100,000th, right? I mean, they differ by a really small amount. You can see the further away we get, the more they differ, right? And I could actually do that to help as well. And you could do it the same with the table at do a step of 0.001. You're going to get your calculator to flip out, though, eventually, right? If you say, how about 0.0001, the calculator's just going to start rounding and say, you know what, they're the same thing. But that's because the calculator's not as smart as we are. All right. I have more to show you, but it seems like a good chance to ask some questions.
It sounds like a dumb question, but why do we have to know where the wire they are the same at that point?
So it's really helpful because it means that this tangent line and this function have the same slope. So it actually means we can talk about functions having a slope, which we were never really able to do before. We can only talk about linear functions having a slope. Now I can ask you, what's the slope of this parabola at x equals 2?
It's just at x equals 2.
Yep.
Because before you find the slope, we would need 2 points.
Right. And before, in pre-calc, you weren't really even finding the slope. You were finding, for a parabola, you were finding what we call the average rate of change, which was that line. And now I'm saying, you only need 1 point to find the slope. How bizarre is that? Now, Leah's complaining. See, it's great that we only need 1 point, but Leah's saying, but that means if you want to find the slope of the function, it's always changing. So you always have to do the problem over and over and over again. And we'll see if we can come up with some shortcuts there.
You need 2 points to find that tangent line to get the slope?
Okay.
Yeah,
So,
initially.
okay. Fine. Let's play the game a little bit. All right. You asked for it. So first of all, let me give you some notation. We call the slope of this function. We call this the slope at x equals 2. We call that the derivative. And derivative is a new vocabulary word that means what's the instantaneous rate of change, or what's the slope at that point. There are 2 ways of notating it. The easiest way is attributed to Newton. Newton would say, find f prime of 2. And that prime, that little apostrophe, means find the slope at x equals 2. So 2 is the input, and the output is not the function, but the slope. Okay? So far, so good? Leibniz, who also did calculus, would have said you could use this notation. Find me, that's bad, sorry, I don't like where I'm writing it. Find me dy dx when x equals 2. Now, Leibniz notation, it's a lot more involved and complicated, and lazy mathematicians don't like it, but can you see why actually as a student, this is actually screaming exactly what we're doing? Do you understand how that notation is a little nicer? Someone tell me why it's nicer.
Because y over x is slope.
It's change in y, change in x. So it's not really, it's not a separate d and a y, it's a dy. So they come together. You can't separate them. But what it stands for is a differential in y. And a differential is Not like a delta, it's a teeny tiny change. Okay? So Leibniz says, what's a teeny tiny change in y over a teeny tiny change in x? And this is where, like Krista and Leah were saying, see, you needed 2 points if you want to find that teeny tiny change. All right, you ready?
Yeah.
No, Caroline's like, no way. All right, so here's what I'm going to do. Instead of looking at, let's look at 2 comma f of 2, right? That's what that point is. Let's look at a point that's really close to 2 comma f of 2. Now, yesterday you told me it was 2.01, right? Yes? Today I'm going to say, let's call it 2 plus h. What's h?
Very small number.
Something small. What do you want it to be? 0.01? 0.001? All right. What's the corresponding y value that goes with 2 plus h? F of 2 plus h. I'm going to use this. I'm going to find the slope between these 2 points. You ready? Caroline's still not ready. Okay. So, I want to do f of 2 plus h minus f of 2 all over 2 plus h minus 2. Does that look like the slope formula? Does that look like rate of change from yesterday, from last year, from the homework? Like, we've been doing this without telling you why for a little while now. We're telling you why now. Okay, this is the slope formula. This is called the derivative. This is also called the difference quotient. Difference because we're subtracting, quotient because we're dividing. I'm going to stick something out in front that we've never stuck out in front before. Okay. H is getting really, really small. It's not 0.1, it's not 0.01, it's not 0.001, it's a teeny tiny number, and now we know why we did work with limits. Okay, this is not for the algebraically faint of heart. I need to do this. I'll tell you what. I will do half of the problem for you. I will do the denominator. All right. You caught me. I need to do the numerator now.
Oh.
All right, so I need to do f. The input's 2 plus h here, and the input's 2 here. What was the function? What was the function? X squared plus 1. So can someone step me through the numerator?
Yeah. It's f of h over, it's f.
It is not.
2 plus h squared plus 1.
Okay, so, Mike, when the input is 2 plus h, and let's see, I'm going to try, hold on. I'm going to do this. I'm going to do this f of 2 plus h in green. And when we plug 2... Sorry. Thank you. F of 2 plus h in green. Mike says when we plug that in, we get 2 plus h squared plus 1. Do people see how when 2 plus h is the input, 2 plus h quantity squared plus 1 is the output by this rule? Do you want to ask a question on that? Is that okay? All right, Mike, call on someone to tell me what the output is when we plug 2 in. I'm going to go back to blue for 2.
5.
We just get 5? Is that all right?
Wait, what do we plug 2 into?
It's 2 squared plus 1.
But now the 5's cancel.
Hold on, I'm not there yet. You loved algebra 2, I can tell. Are we okay? Now, Leah's going to say, yeah, but this is going to change every time you have a different function, right? Right, every time you have a different rule, this is going to change. What's not going to change, though, is the beauty of algebra is always going to unfold. Watch the beauty of algebra unfold. It's amazing. 4 plus 2h, nope, 4h, plus h squared, plus 1 minus 5, all over h. You ready for part 1 of the beauty to unfold? 4 plus 1 minus 5, they go. Okay? And I'm going to factor out an h, and I'm going to be left with 4 plus h over h. The beauty of algebra will continue to unfold. limit as h goes to 0 of 4 plus h equals 4. So I just found out that the slope at 2 is 4. So I could say that the derivative at 2 equals 4. That's one way of saying the notation. Or I could say dy dx when x equals 2 is equal to 4. That's another way of saying it. But basically, we only took one point, 2 comma 5, and we fabricated another point,
I like this.
2 plus h, f of 2 plus h. So 1 point, and we were able to find the slope of that function. We should do more practice, but this is a great time to ask questions because we just did the whole first semester in a day. We're going to do a lot more with this, but this was a huge, huge step. Go ahead.
Well, just from the beginning, why can't we do the algebra out? Like, f times 2 plus h.
It's not f times 2 plus h. It's function notation. 2 plus h is the input into this rule.
So how do we get the second one? How do we get 2 plus h squared? Like,
Because the rule...
What do we plug in, though? What number?
2 plus h is the x. So then
We-
you do 2 plus h squared.
Okay.
Right?
plus
Okay.
So if it were a smiley face, the output would be smiley face squared plus 1.
I didn't see what
Okay.
I didn't see that first equation. So.
Okay.
I said
Something else? Anything else? Now, just out of curiosity, if we took a different point, instead of 2, f of 2, if we took 3, if we wanted to find the slope at 3, what would change? And this is going to be a whole lot easier for me on this than it is going to be on you, for you. What's going to change if I want 3 at the slope at, or if I want this, the derivative at 3? What changes and what stays the same in all my work? Give me some things that change. Shelley, was that a hand in the air or no? No, sorry. You're allowed to scratch. Scratching's good. Chris, what's going to change? If I want the slope at 3, all of a sudden, didn't want that to happen. No, I'm alright. All of my 2's become 3's. I again will do the denominator. I again will do the denominator. You're going to get h. Here we're going to get 3, and then when we plug 3 in, that's 10. Alright. Watch, yet again, I changed the point, but watch how the beauty of algebra is going to unfold. 9 plus 6h plus h squared plus 1 minus 10. Guess what happens?
the numbers cross out. Doesn't make any sense. The numbers directly
Alright. Now, I have a question. Does anyone see a pattern yet or no?
I do. It's twice, yeah.
The slope is twice the number. Wow. I wonder if that's always true.
With a parabola.
any parabola or this parabola? I don't know.
I bet you do know.
Okay. Can I try doing this problem again? I'm going to do this. Instead of picking the point 2, I'm going to pick the point x, f of x. And what's a point that's really close to x? X plus h. Whoops. F of x plus h. Alright, this is not for the algebraically faint at heart. Okay, you ready? We get f of x plus h minus f of x all over x plus h minus x. This is called the definition of the derivative. It's also called the difference of the
differential quotient.
It's called the difference quotient. It's also called the instantaneous rate of change. But when I say use the definition of the derivative to find the slope, it doesn't mean picking numbers. It doesn't mean like zooming in. It means using the definition either like we did here or like we did here when we picked a number. All right. Once again, I will do the denominator. All right, Krista, what happens when I plug x plus h into the function for the input? What do I get out?
You're going to get x plus h times x plus h.
All right, I'm going to call it x plus h squared.
Okay.
Plus 1. Good. You see how that works? Good. No, I know. I didn't. I was checking in with you. Good. And when I plug x in, I'm going to get x squared plus 1. Is that okay?
Yeah.
All right. Are you ready to watch the beauty of algebra unfold?
Maybe.
X squared plus 2xh plus h squared plus 1 minus x squared minus 1. The ones cancel. X squareds cancel.
Take out an h.
Take out an h.
2x plus h. Over h, the h is cancelled.
H's go.
2x plus h equals 0, or whatever we're saying.
Oh, sorry. The limit as h goes to 0 is just equal to
2x plus h.
when h goes to 0?
2x.
2x. Didn't you just tell me that the rule was it was always going to be double the amount? Whatever the x is, it should be double?
You did that.
I think, yeah, I did maybe. But, so this is the difference between finding a rule for the function, right? So we actually can say that the derivative for any x is equal to 2x. Now that's only true for that function. Now you're generalizing a little bit. For this parabola, all right? And the question is, well, actually the question, no, I'm not ready for that question yet.
Negative of the x squared.
Yeah.
So the limit of not every parabola is twice the slope of the not every.
No, the vocabulary there was completely out of order. For the function x squared plus 1, which happens to be a parabola, the slope at any point is twice the x value. So if I asked you for x squared plus 1, no. On this parabola, if I asked you what's the slope on this parabola when x is 10, you would tell me?
20.
Yeah. How about when x is equal to pi?
2
Oh, yeah, very good.
None of this won't play into role
No.
in any other parabola.
Well, I have a question. What would change if the function was x squared plus 2? How would that compare to the function that we were looking at? Whoops. What's the difference? No, I'm just asking what the... Never mind. I'm not ready for this question. Okay, so... Maybe.
That's what I was thinking.
All right, so I want to recap a little bit. First, you can use tables or values that are close together. Okay, that's like a numerical method. Like, so if I asked you to approximate the derivative using a table, you could pick 2 points that are really close together. Does that seem like what we did sort of yesterday and a little bit today? Okay. Another thing you can do is use the definition of the derivative. Whoops. Got a little too excited there. Definition. ION. And the definition of the derivative is something very, very special. It's the limit of the difference quotient. And it's also, the other thing we say, it's also the analytical or algebraic way of doing it. We didn't really do too much with the calculator today. I think I'm going to shy away from the calculator for at least a couple days, and then I'll show you, actually, there are a few more methods that your calculator can do, which is sort of nice. So can I ask, as we look at it, if we look at like, I'm not asking for the answer, but if we looked at 5 for this table, and I asked you to approximate the derivative, see that new notation, at 4, could you use a table to do that? If you use these 2 points, we say that it's a right-hand approximation because it's 4 and a little bit above 4. If we were to change our minds and use these 2 points, it would be a left-hand approximation. That, if you, I love, gosh, this is great. If you used, come on, this point and this point, this is called a symmetric difference quotient. You're using both sides to do it, and it should be true that the right-hand side should either be a little bit high or a little bit low. The left-hand side should be the opposite, a little bit low or a little bit high, I guess depending. And then the symmetric difference would actually be somewhere in the middle. It might not be exact, but it might be a better average. Yeah. Or, oh, go ahead, Christina.
Didn't you use like 2 of the points and put them in, what's the format when you do like y1 minus?
Yeah.
And you do that, and then you plug in the like 4 plus h and like find the exact, like what we were just doing?
No. Because once I give you, you don't have a function. You don't know what the rule is.
But that's what you'd be getting is the function, wouldn't you?
No, you're just be getting a line that's sort of like the function, and once you're doing that, you're just coming up with a slope anyhow. All right. Yeah, go ahead. I think.
What did you call it when you used the first and the last slide?
It's like a symmetric difference quotient. It's like a symmetric way of trying to find the slope. A little bit to the left, a little bit to the right. All right. Excellent work. I could not be more impressed with the questions you're asking and the answers you're coming up with. Have a wonderful Wednesday. I'll see you tomorrow. Will I see you tomorrow? Yeah, I'll see you tomorrow. I won't see Krista tomorrow.